Hi everyone. Today I have a novel little circuit to look at. It's a nice little hobby circuit that allows you to do a lot of different things. This can actually run a motor with one coil, and you don't need a trigger or a reed switch or Hall effect sensor for the switching. And what's kind of neat about it is it'll run all these things over here. Monopole. It'll self-oscillate with some air cores. You know, my standard stator motors, this is would be a 2-coil. Here's some three-phase motors that are right off of the printer circuit boards. These aren't even modified, so you know, naturally they're 3-phase. It'll run the window motor, any of them, and surprise, it'll even run a model airplane motor. And so it's not going to run 3-phase, but let me explain what's going on. Here's a window motor that's been running on a part of this circuit. It's just the simplest form, and it's been running since last week sometime on a capacitor. And if you take a look here, you can see how simple this circuit can be made. We'll get to that in just a little bit, but let's talk a little bit about where this thing came from. So here you can see the circuit that I was showing you. This down here is the circuit you see in the simplest form, with the 2 transistors and the biasing resistors and the battery. And here's your motor coil. Alright? And that's what you saw running on the table here. So if you look above, you can see that same circuit here and over here on this side. Now, so you know that it runs here on the single circuit, but look what's happening over here. This L1, 2, and 3 is actually a 3-phase motor. So one side of the circuit pulses 1 phase and goes out through this 3rd phase, and then when the magnet goes over L2, it pulses that phase along with going back over L3, and that actually makes the motor run. Believe it or not. And if you're going to run a bi-feller motor, just 2 coils, you only need L1 and L2, and you just jumper this over to the positive side of the battery. So we're going to show both of those. Now if you want to run just one motor, you don't even need one side of the circuit. Just plug your single coil into one side or the other and you're running. So let's have a look at some of this stuff and see what you think. Okay, so I'm going to go back to looking at this circuit, and that's just about as simple as you can possibly get it. And that's running here, as you can see. Almost can't find the circuit, but there it is. And that's my little MPS A56 and MPS A06, PNP and NPN. And like I said, this has been running for, I don't know, 4 or 5 days, 6, I don't even remember. And that's the capacitor voltage. And the last digit there that's flickering is, I don't know, I think 100,000th of a volt. I don't know, I forget, 5 decimal points. So you can see that that's almost using nothing at all, and I don't know, maybe that'd run a couple weeks, but so that's as simple as it gets. And it can go a little faster, well, whatever voltage you want to put on it. Okay, so I put 2 AA batteries on there, and you can see that the motor picked up speed pretty good. And voltage may drop a little bit until the battery stabilizes, but as you can see, it's it's going to draw a little more current with more voltage if I don't make adjustments on those resistors. So I don't know, you want to see it go a little faster, right? Hold on, I'll hook up a power supply and we'll take a look. Okay, so I hook up the power supply here, and I'm running at a little over 3 volts, and I've got nothing going on as far as the digital amp meter is showing. So I'm going to turn this up until I get something to show here. Okay, I'm going to go to 9 volts, 9.2, that's like a good fresh 9 volt battery. I'm still drawing only 10 milliamps. And look here, I'm going pretty good. Now this is something I just don't get with the self-starting solar circuits. But right now, okay, before I start anything, I have to show you this. This is Remington, and he's hiding from the squirrels. I'm not torturing him, putting this around him. He does this himself. And then when a squirrel comes around, he comes out and barks, and we're supposed to let him out to chase the squirrel. So he's a clever guy. Oh, I almost forgot. Just in case you really can't see him. There he is. Okay, Ram? You're going to have to help Daddy make a movie, so get ready for that, okay? Okay, come on, Ram. Time to get back to work. You going to help Daddy now, huh? It's a serious business, you know. Okay. Oh, you just want to get your belly rubbed on, that's it. Okay, so now I plugged in the familiar old stator motor, and on this motor there was 2 trigger coils and 2 power coils. So that happens to work out perfect for what we want to do here. So I've got the 2 power coils plug into the board here, and let's take a look at that on the computer. Okay, so now we're looking over here. Remember I told you this was a 3-phase motor, but we're hooking up this bifilar stator motor, and we have L1 and L2. We don't have an L3, so let's just take care of that right now. And now you can see we sort of have a center tap, and we go back over to plus. So what should happen here, since these 2 are firing at the same time, that's sort of not the same thing as using a 3-phase motor. So I don't know what this is going to be like, sort of like a one of the SSG circuits or something. It should look similar. Okay, before we go on with this test, let me tell you that this Q1 and Q2, the MPNs, I've switched into something a little stronger, and that's the BD 243C NPN. That's popular on some of the Bedini projects. Q3 and Q4 is still the MPSA 56, and if you looked at this parts list earlier, I had a mistake here and I had 06, so if you copied anything from the first list, make sure you cross that out and add this PNP in there, the MPSA 56. And of course, here's our other resistors and stuff. But anyhow, so we're running now with a little bit heftier transistors. We have some neon lights and the neon bulbs in the circuit. And so here we go. Oh, forgot to tell you, we've got a scope hooked up too. And that's going over here to the outputs of the diodes and over to the negative rail. I don't have any charging batteries in here yet, but you know, maybe we'll do that pretty quick. We'll see. But anyhow, we're running at 5 volts, 5.2 volts, 60 or 70 milliamps, and motor's going around, come on, John, 1100 RPMs. And look what we have on our scope. So we're only at 5 volts. Let's take a look at this. This will be interesting to you. We're running at 5 volts. And I have 5 volts per division, and I'm on ×1. So we're running at 5, and look at this peak, this generated voltage of 10. A little bit more, actually. It might be 12. And then there's some radiant energy, if we call it that, or back EMF. So that says a lot. What's interesting about this is a voltage that has some current, and this has radiant. So we've doubled the voltage. I know everybody's saying right now that they're going to call in or write in and say it's a boost converter. Well, maybe it is a mechanical boost converter, but I mean, you can call it whatever you want to call it. You could call it a 2-stage single coil boost amplified radiant oscillator magneto motor generator driver charger. But I don't even know if that all covers it. But anyhow, we're only running at 5 volts right now. So what happens if we kick the voltage up? Let's see where the... Yeah, well, let's try it. You can hear the motor speeding up. I'm at 9 volts now, drawing 200 milliamps. Take a look at this, people. Neon bulbs are on. Starting to look like Bedini's in the house, huh? Okay, so alright, we get back to this thing that looks like a mechanical oscillator boost circuit or something, and see what we have here. I'll never get this stabilized. The scope isn't working very good. Anyhow, so now we're at 9 volts. Let's just go to 10. That makes the easiest. So there's 10 volts, drawing 160 milliamps. I've got 5, 10, 15, 20, 25 volts on the output that's carrying current, and something way above here yet on the radiant. If I switch over to 10 times on the scale, we'll see what that is. It's not going to be real high, but okay, so it's on times 10 now, and we're about 150 volts of radiant, with still at 25 of something that's a little bit more in current. So let's see, what can that do? I've got a funny feeling that we should be able to really charge a capacitor. I'll go back to ×1 scale. Okay. And what do we got for RPMs out of curiosity? Can we see that? 3,000 RPMs. I'm telling you, that thing is smooth. I don't even know if you can hear it running. Probably doesn't have much power. Got a little bit of power. Let's see what happens to the current when I stall it. That current goes up to about 200. Okay, we get a capacitor. Alright, I'm going to try to get this so you can see the scope and the capacitor both. Here's the cap. I don't know if I can move this over any better. But let's see, it should charge at 25 volts really quick and then slowly charge the radiant. Oh yeah, exactly. Ooh. I don't know if you're going to get a chance to see any of these or not. Wait, I think, let me see if I can do this some other way here. There you see a charge. It's charging with the radiant. You can see that first 25 volts goes really quick. I'm hoping to get a good spark in there that you can see. Let the radiant charge it up a little bit here. That's pretty snappy. I guess maybe I can zoom down on that a little bit. Okay, so we can see it charges the capacitor pretty quick. Now, I'm not saying anything about the circuit. I just think it's fun to experiment. It might be interesting for somebody who really has good luck with a cap dump circuit, like maybe Patrick or somebody. But anyhow. So let's go on and see what it'll do with a battery. I'll hook that up and we'll take a look at that. Decided they're going to try this circuit. They're probably going to try to charge some batteries. So there's 24 volts there. And I think I'm all hooked up here. I have the power supply on 12 volts and limited to 0.5 amp just in case. And the 24 volt battery is 23.89, almost 23.9. And let's get started here. So we're on our way. And I must be over 0.5 amp. No. Alright, I'm using 260 milliamps and charging. You know, I don't want you to think this battery is actually charging this fast because these have been sitting, so you know, it's going to charge pretty quick until it gets up to a certain point, and then it'll slow down some. But it does charge. Probably could make it a little less confusing. Let me set a couple things here. Alright, so you can see it'll charge. I think that probably could charge with a little more current. So I'm going to turn this up a little bit and see what it does. I'll go to 400 milliamps. That's charging pretty respectively now. I had to go up in voltage and see what I'm at. 13.5. But as you can see, because of the step-up voltage of the motor here, whereby it sort of acts like a boost converter, it also wants to draw a little bit more current. So, but this is kind of interesting here. It's drawing 400 milliamps. And if I were to draw 400 milliamps without these batteries on, these transistors would be hot. They're not even warm to the touch. There's nothing going on for heat here. They might be, I don't know, maybe 5 degrees above room temperature. So that's pretty interesting. I'm not sure what to make of that, but they're cool as a cucumber. Alright, so I guess that shows it can charge a battery. She's still going pretty good here. Need to move on to something else. It's going to get too long. Okay, going to try a different motor. Okay, this should be fun. This is a standard printer motor, and it's just fresh off of a board and has had no modifications at all. And so naturally these are 3-phase. You'll find 3 wires that you can hook up to. I'm down here on the circuit board with the plug, and here's the 3 wires, 1, 2, and 3, and they correspond with up here, which would be 1, 2, and 3. And here's the 3 coils in the motor. So happens that I explained before, but the 3rd phase is going back to plus battery. So I'm set at 12 volts, and I'm going to give that a little pop. Yep, it goes both ways. That's something that 3-phase doesn't do, right? Okay, so there you go. So off she goes without a 3-phase speed control. Let me just check the speed that I'm getting here at 12 volts. You can see it. 3,630 couple. 3,000 RPMs is not bad. And we're drawing 170 milliamps, which is not much at all for a 3-phase motor. Some of these 3-phase motors with speed controls can run up over an amp while they're idling. Alright, so 12 volts, there she's going. Now, you're probably wondering what's coming off of this thing, so let's take a look over here. I have the scope on here. And have a look. So the scope is set on 5 volts, And so we're 5, 10, 15, 20, 25, 30 volts of a sort of a rectified sine or whatever. It's the output from the diodes. But take a look. I mean, this is current. This up here is like radiant, and this goes up to 150 volts if I switch it over to times 10. But this is what's interesting. So there's, once again, a very similar effect that you'd kind of expect if it were a boost converter, I think. But anyhow, so sure, you'd probably say, well, that charge a battery? So let's put the battery in here. Here we go. Heard it slow way down. And I don't know if it went down at first, but let's make sure we're not drawing too much current. 330 milliamps, that's not bad. And yeah, sure. So, you know, we just pulled a motor off a board, plugged it into this circuit that you can make for a couple of bucks, and it does look similar to a John Bedini experiment. But you know, keep it in mind, people, if you've studied John's work, you can't get anywhere charging with current and radiant at the same time. But you know, there's a way around that too by using cap dumps and so on. So you have to be up on that a little bit to fully understand. But all right, so there's a cute little deal for you. I'll unplug this charge battery again. You can see it does slow the motor down. Don't get too excited about this because there's not a great deal of power here. There's a little bit there, but when you slow it down, you're still not drawing too much current, so you can't really expect to have too much power either. So I've got an idea that there's a way around that. I'll have to experiment a little bit. But let's just try a couple other motors before we run into too much time. I'm going to switch over. I don't have enough hands for that. Here's another one fresh off a board. so, you know. Oh, that's my cord rubbing on the shaft over here. So anyhow, that's doing and looking the same. The scope isn't stabilized, but you can see it's still up there in voltage. Far less radiant. See maybe I should try to stabilize that. Hold on a minute. Alright, so there you can see that there's far less radiant or high voltage back EMF on it. My guess is that there's different windings, fewer windings, and it kind of shows up that way. So, but and you know, nevertheless, I plugged it right in and it just started working. So let's go on to another one. Okay, so I knew that you knew that I was going to finally get to this. Here's a model airplane motor, and this was a Scorpion kit that I modified to change the eddy current paths a little bit. That's why it looks a little bit unusual on the flux ring. And well, that's another video. It worked out so-so. But at any rate, so what you have here is a motor that has very few turns. I don't even remember what this was, like maybe only 10 turns or something. And so it's a little harder to start because naturally with this circuit you have to develop something, you know, to fire the transistor. So, alright, I was surprised when this worked, but here, have a look. Now the bearings are a little bad on there, and so you're going to hear that rattling, but running at 12 volts and drawing 430 milliamps, and RPMs are 11,300 something. 11,300. So that baby's really cranking. Now there's not a real lot of for less than half an amp, you know, there shouldn't be anything, but there is a little bit there. You can see that as I stall the motor, it doesn't go jumping up over several amps. Let me give it more current just in case and find out. No, that's about it. Alright, but now I can even smell there's a little bit of heat here. Yeah, there is some, so I need to cut that back. That's a shame, isn't it? Alright, you talked me into it. I'm going to throw a couple of heat sinks on there, jury rig them, and let's see what we can do. I can go up to 20 volts instead of 12, so hold on, let me get that ready. We'll take a look. Okay, so here's the tool and die version of a heat sink, and we're going pretty good here. I'm going to crank it all the way up and see if I can do this without burning anything out or throwing something off the motor. I know that baby's cranking. Let's see. So there you go. I want to call it 20,000. Alright. Anyhow, she's going good. It's only drawing 670 milliamps. Of course, that's not going to get hot. Ooh. Ow, it's hot. Now, okay, so it doesn't even draw an amp. Now, if we slow that down so we can hear. Alright, so that didn't even draw an amp. So there, you know, there could be some use for this circuit, but what would have to happen is you'd probably have to change the driver transistor to maybe an FET or something, you know, that turns on hard and stays on. Because what I think is happening is when you stall the motor, you slow the motor down in RPMs. When you slow the RPMs down, your driver transistor isn't turning on as hard, so you don't draw excess current then when you're stalling it, because you're slowing it down and you just don't have the drive. At least that's a probability. So, like I said, this circuit is an infant, and it was the first thing that I've been trying with it. And you know, there's no protection in the circuit, no protection diodes. There's not even a capacitor in this circuit. I have to tell you, if you're going to experiment with this circuit, you should be using a power supply that has current limiting, or you should have a fuse on your battery, or you should be using a tiny battery at first that you're not going to blow things up with, because here's what happens if you're not careful. This is what a transistor looks like when they go off like a firecracker. So this circuit is, you know, it's risky because, you know, it's not too forgiving if you make mistakes. So I can't be held responsible for this being up here and you looking at it and you copying it. But I'm just saying, you need to be careful, okay? So anyhow, I hope you enjoyed the videos, and I'll see you next time around. Take care, everybody.